Okay. So different forms of hydrogen. The first one is going to be atomic hydrogen. So what is going to be the atomic hydrogen? When we are going to take the hydrogen molecule, how we are going to get this one? So when we are going to make electric arc on to a hydrogen molecule, so this hydrogen bond which is present, it is going to be cleave and it is going to give two hydrogen atoms. For this, the energy required is equal to 435.9 kilojoules of energy. How much energy is required? 435.9 kilojoules of energy is going to be required for breaking this one. That is going to be supplied by an electric arc. We are going to supply this much energy by making an electric arc. These two hydrogens are going to be get separated into atomic hydrogen. So this is going to be called as atomic hydrogen. So this atomic hydrogen is going to be highly reactive. This atomic hydrogen is going to be highly reactive. Why it is going to be highly reactive? As this hydrogen is going to be formed by the supply of 435.9 kilojoules of energy, this hydrogen is going to be highly reactive. This highly reactive hydrogen is going to have only the lifetime is 0.3 seconds, 1/3 of second. 1/3 of second is going to be the lifetime of this hydrogen. Immediately it is getting to be combined and again it is going to be forming the H2 molecule back. Understand what I said? Atomic hydrogen is going to be formed by the breaking of H2 molecule and it is going to be giving the two atomic hydrogens by breaking the supply of this much of energy, 435.9 kilojoules of energy. And now the formed hydrogen is going to be highly reactive because it is going to be excited. So 435.9 kilojoules of energy we are given. So obviously it is going to be get excited, isn't it? Energy whenever it is going to be taken up by any particular element from ground state to it is going to be get excited. So excited state with high energy always going to be less stable. Less stable is always going to be more reactive. That's why this atomic hydrogen is going to have more reactivity than the normal hydrogen. And this atomic hydrogen lifetime is only 0.3 seconds. 1/3 of second is only going to be the lifetime of this hydrogen. Again it is going to be combined to form H2 molecule. Whenever these two hydrogen atoms are going to be combining and forming the H2 molecule, they are going to be liberating the 435.9 kilojoules of energy. So this much energy as it is liberating, we can able to use this one for the welding purpose. This particular hydrogen is going to be exothermic now. The formation of atomic hydrogen is endothermic. It is using the energy of 435.9 and it is going to have only the lifetime of 0.3 second. But now this hydrogen is going to be combined after 1/3 second. It is going to be liberating this much huge amount of energy. That's why we can able to use this one for welding purposes, this atomic hydrogen. And moreover, it is going to be reactive. That's why it is going to be used for reducing ability or hydrogenation chances we are having. So that is the purpose we are going to discuss atomic hydrogen as a separate form of hydrogen. And the next one we are going to have nascent hydrogen. The next form of hydrogen is nascent hydrogen. What is the meaning of nascent hydrogen and atomic hydrogen? Atomic hydrogen we are representing like only H atom. But nascent hydrogen we are going to write it with a square bracket. That is going to be indicating more reactive than that atomic hydrogen. So how we are going to get this one? When we are going to take zinc plus H2SO4. So this is going to be liberating the two hydrogens which are going to be present in nascent hydrogen form. So that whenever we are going to write a square bracket on any element, that is going to be indicating highly energized. That highly energized nascent hydrogen is going to be more reactive. It is going to have high reducing ability. This nascent hydrogen is going to have high reducing ability. So we are going to get ZnSO4. That is not the requirement for us now. So that's why I'm not discussing about this one. The nascent hydrogen which is liberated by the action of zinc on H2SO4 is going to have high reducing ability. Reducing ability is going to be very much high. So because of this reducing ability of nascent hydrogen, it can able to show certain properties like highly oxidizing nature compounds what you are having, KMnO4 and K2Cr2O7. Your KMnO4 color can be decolorized. Your K2Cr2O7 dichromate orange color is going to be get converted to green color, and also we are able to get reducing whatever the properties you are having. Say for example FeCl3, which is going to be get converted to FeCl2, colorless. So all these things are going to be formed by your nascent hydrogen. So what are the things we can able to see from here? This H can able to do FeCl3 is going to be get converted to FeCl2 plus HCl. So yellow color of FeCl3 is going to be loose and we are going to become colorless. Understand? So this is the reducing ability of nascent hydrogen. The nascent hydrogen which is produced by the metal action on sulfuric acid. Usually zinc we are going to use. Zinc plus H2SO4 is producing the form of nascent hydrogen. This nascent hydrogen is having the reducing ability. So what is the example for reducing ability we are going to have? FeCl3 ferric chloride yellow color is not going to be there. When it is reacting with your nascent hydrogen, it is becoming colorless. So this is the one, and we are going to have the same nascent hydrogen is going to be get converted to K2Cr2O7 potassium dichromate in presence of sulfuric acid. It is going to be converting chromium sulfate SO4 thrice and K2SO4 plus H2O we are going to get. Some 6 hydrogens are going to be used in this reaction. 6 nascent hydrogens are going to be converting your orange dichromate into your green color chromium sulfate. Okay, is it visible? Yeah, fine. So orange color dichromate is going to be get converted to green color chromium sulfate by the nascent hydrogen. So these are actually considered as strong oxidizing agents. These strong oxidizing agents are also get converted to their reduced form by the your nascent hydrogen. That much strong reducing ability your nascent hydrogen is going to have. And one more I said no, the violet color of KMnO4 is going to be get decolorized. KMnO4 is going to have violet color. As we discussed Bayer's reagent, that Bayer's reagent is going to be losing the color. That is nothing but the test for unsaturation. So this hydrogen also can able to be making that particular one to get converting your violet color of KMnO4 to colorless KMnO4 solution. So these are all the examples we can able to discuss for the reducing ability shown by your nascent hydrogen. So that's what we are going to have. The 2 forms of hydrogen was over, and now the next form of hydrogen. So is it clear for everyone? The different forms of hydrogen we are discussing now. So the first one we discussed atomic hydrogen, which is going to be formed by the particular electric arc when you are going to apply between the hydrogen atoms of a molecule. We are going to get the 2 hydrogen atoms. So those 2 hydrogen atoms are going to be very much reactive, and their lifetime is only 1/3 second. So that's why it is going to be highly reactive, where we are going to be using for making the reaction. It is going to be atomic hydrogen is involving. And the next we discussed is nascent hydrogen. So the nascent hydrogen is going to be produced by a zinc metal acting on sulfuric acid. That is going to be liberating the nascent hydrogen. That nascent hydrogen can have high reducing ability. That reducing ability we tested with FeCl3 get converted to colorless, dichromate get converted to chromium sulfate, the green color, and the violet color of KMnO4 is going to be get converted to colorless solution. So these are all the reducing abilities which are shown by your nascent hydrogen. And the next form of hydrogen, adsorbed hydrogen. The next one is going to be adsorbed hydrogen. What is the meaning of adsorbed hydrogen? Whenever we are going to take the hydrogenation reaction or the reduction reaction, obviously we are going to use metal along with hydrogen. Metal along with hydrogen. Say for example, we are going to take a platinum black. We are going to take platinum black. So the platinum black is a metal. When it is going to be taken up the hydrogen, so what we are able to say this one, this hydrogen gas is going to be adsorbed on the surface of your metal. So the platinum black metal is going to be get adsorbing the hydrogen gas on the surface of its platinum black. So this hydrogen can able to do many chemical modifications like hydrogenation reaction where you want. Say for example, in alkanes we discussed Sabatier-Sanderens reaction. How we are going to get? In presence of nickel, platinum, palladium, we are going to take the hydrogen. That hydrogen is going to be making the hydrogenation of alkene or alkyne to get converting into alkane. This is what we discussed now, the Sabatier-Sanderens reaction. In the same way, wherever we want the hydrogenation or a reduction, we are going to take a metal with hydrogen. So the platinum black, when we are going to take on that, the hydrogen molecule gas is going to be adsorbed. So that's why this is going to be called as adsorbed form of hydrogen. So that's what we can able to say. When we are going to take palladium, this one process is going to be called as occlusion. This is going to be adsorbed hydrogen, but the palladium is going to be called as occlusion. That is, intensity of adsorption is more. Just we can say intensity of adsorption is more. That is only thing we can say. The process we are using occluded hydrogen. Understand? Adsorbed form of hydrogen and occluded form of hydrogen, both of them are going to be useful for the hydrogenation or reduction reaction. So these two are going to be an example for adsorption. So this palladium occlusion, we can able to have a proof, like even in dark also it can able to be combining with halogens. H2 plus Cl2 gives rise to HCl. It is not going to be happen normally, but when we are going to take the platinum, we are going to make it at room temperature, whereas even in dark also we can able to make this hydrogenation reaction with halogens in dark because of this palladium, because occlusion. What is the meaning of occlusion? That is, more amount of adsorption is taking place on the metal surface, which is going to be called as occlusion. Almost 5 times more than its volume, the palladium can able to be adsorbing the hydrogen. So that's why it is going to be called as with a special term occlusion. Normal adsorption means accumulation of any particular particles on the surface of any particular substance is going to be called as adsorption. It is also adsorption only, but it is going to have more intensified adsorption. That means more than its volume, 5 times is going to be adsorbing on the surface of your palladium. That's why the process is called as occlusion. So this is going to be adsorbed hydrogen. This is the next form of hydrogen. And next one, the fourth one, your hydrogen molecule is going to be existing as ortho and para. The hydrogen molecule is going to be existing as two types of hydrogens, that is going to be ortho and para hydrogens. So what these two are? Simply I can able to say they are going to be nuclear spin isomers. What I can say simply, they are going to be nuclear spin isomers. Ortho hydrogen and para hydrogen are nuclear spin isomers. Why they are called as nuclear spin isomers? Your hydrogen molecule is going to have the two hydrogen atoms. The two hydrogen atoms, each one is going to have one electron and one proton, isn't it? Hydrogen is going to have one H1. We discussed already, proton number is 1. It means it is going to have one proton. Whereas they are going to have one electron in its orbit. So that we are going to have one electron, one proton when we are taking one hydrogen atom. When we are going to take hydrogen molecule, it is going to be consisting of two hydrogen atoms. Each hydrogen atom is going to have one electron, one proton. So now the proton is also having the spin and electron is also having the spin. Now, till now we discussed regarding the spin of electron, but here we are going to discuss the spin of proton. Why? Because only one proton is there in your hydrogen atom. So there we are going to have the spin of proton. The spin of proton is going to be same direction. If the spin of both protons are going to be in same direction, this is going to be called as ortho hydrogen. If the spin of the two hydrogen atoms is going to be opposite, is it clear now for everyone? Where I am writing the arrow mark, that is indicating the spin of proton. Now both spins are going to be in same direction. That is going to be called as ortho hydrogen. If the spin of both protons are going to be opposite to one another, it's going to be called as para hydrogen. Understand? So ortho hydrogen is going to be the spin of the two protons is in same direction. Whereas the spin of both protons are opposite to one another, then it is going to be called as para hydrogen. So where they are having the difference? The spin of nucleus. Proton is nothing but nucleus. So the proton is going to have the spin difference. That's why they are going to be called as nuclear spin isomers. The ortho hydrogen and para hydrogen are said to be nuclear spin isomers because they are having the difference in their nuclear spin. One is going to have same spin, that is both of the protons present in a hydrogen molecule will show same spin. That's why it is called as ortho hydrogen. Whereas the para hydrogen is going to have opposite spin. One is going to be showing clockwise, another one is going to be showing anti-clockwise. That's why it is going to be called as para hydrogen. Out of this ortho hydrogen and para hydrogen, which is going to be more stable? Ortho hydrogen is going to be more stable than para hydrogen. When they are going to be asking the question, which hydrogen is going to be more at room temperature, which hydrogen is going to be more at absolute temperature? That's what the question we are able to get. 75% ortho is going to be present at room temperature. 75% is going to be present at room temperature in ortho form. Whereas para is going to be 100% at absolute zero. Absolute temperature. When we are going to take absolute zero, absolute temperature, then we can able to get 100% form of hydrogen is existing in para hydrogen form. Whereas ortho hydrogen at room temperature 75%. But usually when we are going to take, which form of hydrogen is going to be more stable? Ortho form of hydrogen is going to be more stable. That's why it is going to be present at room temperature 75%. It is 75% means obviously the remaining 25% is going to be para hydrogen. But absolute zero when you are going to take 100% para, 0% ortho. So that's what you can able to say. And moreover, these two are going to be called as nuclear spin isomers. And magnetic momentum when we are going to take. So what will be the magnetic momentum of this? So the magnetic momentum when you are going to take for para, it is going to be twice of your proton. The twice of your proton, and this is going to be having the 0. So that's what we can able to say the magnetic momentum of these hydrogens, and that is not at all that much important. But remember, they are going to be having ortho form and para form, that is going to be having the difference in their nuclear spin. The nuclear spin is going to be opposite and parallel. That's what we can able to say about the ortho and para forms of hydrogen. So these are the different forms of hydrogen we are going to have. And now we'll go for the dihydrogen. That is what the most important form of hydrogen we are going to have. So that dihydrogen we are going to discuss. So dihydrogen means H2. So the H2 molecule when we are going to